Good morning, everybody. As we begin our second week of online learning here, I hope you all had a great weekend. This week, we're going to be continuing on in biodiversity and classification. We will have a test on Thursday, so reminder to you all to take good notes. You may use your notes on your tests, quizzes. We'll probably also have a quiz like we did last week on, let's see, it will be Tuesday. We'll do Kahoot this Wednesday. Vocabulary terms due Thursday. We will not do the study guide like we normally do, but there is one in there for practice that you may take a look at. So last week, as you know, we began talking about how organisms are classified. We talked about Carl Linnaeus in the 1700s, who came up with a system of naming an organism using a Latin name. He also put those organisms in groups. And his classification system was based mostly on physical characteristics. He looked at two animals or two plants that looked alike, and if they looked alike, had similar physical characteristics, he grouped them closely together. And today we're going to look at some of the ways we've changed this a little bit. I'm going to move myself up here so you guys can see the slides. So some of his, what we call his traditional methods that Carl Linnaeus and others before him used had some problems. The use of physical similarities alone can be deceiving. So for example, if we look at a dolphin here, you may ask yourself, is this a fish or a mammal? Well, if I'm looking just at physical characteristics, I might say, well, it has fins, it swims in the water, it's probably a fish, right? Most of you probably know, however, that it's a mammal. It has other characteristics such as breathing, gives live birth, things like that that make it more mammal-like. So how do we decide which of these characteristics is most important? Well, that's something we're going to be talking about today. So we call these older methods traditional methods. Here's another example. Which of these three are least like the other? So I have three animals here, a crab, a barnacle, and a limpet. If you look at them, I'm guessing most of you will probably say, all right, the crab is the out group here, right? It has appendages, arms, legs, pinchers, and these other two are shelled organisms. And Carl Linnaeus actually would have agreed with you. He would have said, this is how we're going to classify traditionally. We're going to say the crab, and by the way, this is kind of like a family tree here. The crab is kind of off on its own branch. The barnacle and limpet, because they have shells, are more closely related. However, when we look closer at these, we have found that the crab and the barnacle both share two things that the limpet does not, and that is a molted exoskeleton. In other words, they lose their shell, and they have body segmentation. The limpet has neither. So in the newer version, we have the limpet as the out group and the crab and the barnacle more closely related. This kind of diagram is what's known as a cladogram, and we're going to show you how we make these today. Cladograms are based on these characteristics that we call derived characters, like the molted exoskeleton here, the segmentation, that help us kind of put things in perspective. They're what we call evolutionary innovations, which groups share only if they're closely related. Okay. So today's topic is modern evolutionary classification. The scientific word for it is phylogeny, and you can find this in 1902. By the way, I encourage you to be reading the textbook this week. Make sure you read chapter 19 before the test on Thursday. Modern evolutionary classification is a system of grouping organisms based on their evolutionary descent, not just physical characteristics. Now, that doesn't say physical similarities aren't important, okay? They are important if they are shared because of an evolutionary relationship. However, if they just happen to be the same by chance, then they're not important, okay? Carl Linnaeus in the 1700s was not aware of evolution. Remember, Charles Darwin came around in the 1800s and proposed the theory of evolution. So Linnaeus, as hard work as he did, really didn't understand this idea of evolution and how it could be important in showing relationships. Okay, so shift on here a little bit. Making of a cladogram which is what I just showed you a moment ago, is called cladistic analysis. That's just the fancy word for it. And it's a diagram showing evolutionary relationships, a lot like a family tree, how it might show two siblings or cousins or grandparents, how they're related to one another. A cladogram is really the same idea, but we also put those derived characters in the cladogram, like I just showed you a moment ago. Um, so the word cladogram comes from the word clad, or some people pronounce it clade. A clade is really a group of organisms that all share a single common ancestor. Okay, they're sort of like I don't know, I always think of the word clan, a clan who came from an ancestor. It includes all the living as well as all the extinct organisms, or if it was a family tree, those who had deceased. Um, a clade must be a monophyletic group to be a valid or good quality clade. What that means is that they came from one ancestor and it must include all the descendants. It can't leave anybody out and it can't include anybody who didn't come from that common ancestor. Okay. Can you think of any examples of clades in the animal world or plant world? Okay, well, you may think of things like perhaps the birds. The bird group would be a group. We might think, oh, we got robins, we've got finches, we've got ostriches, right? And they all came from some ancestor that somewhere along the line came up with this idea of wings and feathers as adaptations. Okay, that would be an example of a clade. Now, these wings and feathers and things like that are what we call derived characters. Okay, derived character is an evolutionary innovation. In other words, an adaptation which helps an organism survive, and because it does that, it ends up getting passed on to the descendants. So one example might be a backbone. Okay, we'll look at some others here in a moment. Here's some others. If we look at a lion, we might say, well, it has hair, right? It has retractable claws. If we look at a coyote, we might say, well, it has specialized shearing teeth. Okay. Now, each of them have their own groups or their own characteristics, but we also see some that they both share, right? They both share hair. They both share four limbs. Okay, they both share a backbone. Okay, so that would put them together in a bigger group, a bigger clan. But they also have some that they have only to their group. So, for example, the lion here has the retractable claws, which allows them to keep very, very sharp claws. They're not being worn down on the cement or rocks or sand or whatever they're walking on. Whereas the coyote and other dogs do not have that. So it puts them in different groups. So just like Linnaeus had groups within groups, in other words, large groups like the kingdom, smaller groups like the families and genus and species, we continue that with evolutionary in cladograms, okay? Groups within groups. All right. Now, with these derived characters, whether or not a character is derived depends on the level at which you're grouping organisms. Like we mentioned a moment ago, four limbs, for example, is a derived character for the clade called tetrapoda. Okay, that means four limbs. Hair is a derived character for the clade mammalia, which is a bigger, broader group, right? But four limbs is not derived for mammals. If it were, only mammals would have four limbs. Okay, and we know obviously that there's other members of groups like, let's say, lizards, for example, which have four limbs, but they're not members of the mammal group. So tetrapoda would be a bigger, broader group, maybe like maybe a class, well, let's say an order, and a mammal would be something like a class, okay, a smaller, more distinct group. Okay, one of the problems with derived characters is they can be lost. Okay, we talked about vestigial organs in earlier on, things like our tails and things like that, and losing traits can be deceptive. And the reason is because just because you lost a trait doesn't mean that you're not related at some level. Okay, for example, both whales and snakes have lost the tetrapod character of four limbs, but that doesn't make them closely related. Okay, they may have lost them at different times and for different reasons. So we have to be careful about not having a trait as a trait itself. Okay. Television, we could think. Whoops. Bring myself back there. Television is another example that we could use for evolution. I tried to find some pictures of televisions from different decades and kind of drew a little cladogram here. So here's a 1940s television, black and white. So by the time we get to the 1960s, we have color TV. So one of the derived characters we could have put in here is color, right? By the 1980s, a real big revolution, you guys don't remember this because it was before you were born, but was this little remote control here. Okay, this other TV you had to get up and click the knob back in, well, the 1970s actually. But so now we have the derived character of remote control. And by the 2020 here, obviously we have this flat screen, plasma screen, which also has the color. It also has the remote control. So what happens over time is these derived characters, if they're good successful ones, tend to accumulate in an organism. So we can use those organisms that, or in this case, the TV that has the most accumulation of derived characters as the most modern TV. Okay. So that kind of answers our question here. What happens to derived characters over evolutionary time if they're successful, right? They tend to accumulate. And those that have the most have I guess, evolved the longest, perhaps, okay? Or are basically the newer organisms on an evolutionary time scale. Clades and traditional taxonomic groups. A clade, like we mentioned before, must be monophyletic. What does it mean again? It means it must include the ancestral species and all of its descendants. No species that are not descendants of that ancestor. Okay. Many of our traditional taxonomic groups do not form valid clades. And let me just give you an example of that one. Today's reptiles and today's birds all came from a common ancestor. Okay. However, Linnaean class Reptilia, Carl Linnaeus's class called Reptilia, does not include the birds. So it is not a valid clade. And now we're actually changing it. Now, most of us still don't think of birds as reptiles, but they really are. And let me show you what I mean by that. Okay. I know this is a little small here, but this is over on the left here, Linnaeus's class Reptilia. Okay, notice it includes turtles, lizards, snakes, and crocodiles. However, right here is the birds. And actually, if we look at this, birds are more closely related to crocodiles than crocodiles would be to something like lizards or turtles, right? So since the birds are in this whole group here, which really starts right down here, birds are actually of the Reptilia group. And this next group, the modern version of this, does include birds. We call it clade Reptilia. It includes the birds, okay? Now, we can talk about the birds as their own clade, right? Here's a group within a group. This is clade Aves. Aves means bird. And it's just a smaller group within this larger one of clade Reptilia, okay? So again, Carl Linnaeus didn't know this. Many of you maybe have seen Jurassic Park and heard this already or know a little bit about it, that the birds really are a type of reptile, okay? All right, and this just kind of goes on to talk about that some more. So here's a couple generic examples of clades. This first one here is in green is a clade, because notice it includes all of the organisms that came from this common ancestor here. Here's our common ancestor. That's what we call a branching point or a node. This clade also, a smaller one, has just this branch. That's a true clade. However, down here in red, we see a group that includes some distantly related members that don't include the common ancestor, right? So this would be not a true clade here. Okay, in order to be a clade, we could say the entire thing here is a clade, right? Because it includes that common ancestor. But we can't just pick and choose a few of them and say, wow, you're a clade. Okay, this orange one, this one doesn't involve a big group. Can you tell me why it's not a clade? Why would that one not be a clade? Okay. even though I can't hear you, I kind of know what you're maybe thinking here. We've left out this group here, right? We've left this branch off. So therefore not a clade. If we put the whole thing as orange, then we could say, yeah, it includes the common ancestor here and everything that came from that ancestor. But since we left this one out, it's not a good clade. Here's another example that I want you to think about. Which of these two are least like the other? Or I'm sorry, which of these one is least like the other two? Okay, you may say to yourself here, well, the stork, right? That's out. Turkey vulture and African vulture, both are vultures, and if you know something about vultures, they're both scavengers, so they have a similar type of habitat and niche. However, it turns out that the African vulture here is the out group, and the stork and the turkey vulture are most closely related. Why is that? Well, this is based on DNA similarities. Okay, we now use DNA sequences, and we find these in the nucleus, of course, as all of you know, and as well as the mitochondria. Mitochondria has DNA in it as well, to determine relationships that are sometimes difficult to see from traits alone. Okay, why would, go back to this one here, why would the stork and the turkey vulture have the most closely related DNA? Well, if you know where they live, both of these animals live in North America here, whereas the African vulture lives on the African continent. These two are going to have the most closely related genes because their ancestors lived in the closest location, so therefore they were interbreeding for longer. Okay, the African vulture was geographically isolated from the other two, so they don't have this as similar DNA. Okay, so nowadays, many taxonomists and what we call systematists, who are people who group these organisms, use genes as derived characters. The more derived genes two species share, the more recently they shared a common ancestor. And you might remember the amino acid activity from last chapter, where we went and counted the numbers of amino acid similarities between humans and chimpanzees and bears and things like that. And looking at those similarities, we can actually count how closely related two organisms are. And we can actually use these in a cladogram. Let me show you what I mean by that. Here's a cladogram. It's really the same as what we had before, but it's kind of turned on its side a little bit. We don't even know, I don't even know what these are, if it's a plant or an animal. All I have is a DNA sequence here. So if I look closely and look at this sequence, right, I can see that this one here was the least changed one, or the least numbers of mutations. Okay, if I look at one that's, or two that are similar to it but just have one mutation, this one here has this G mutation. This one down here has a T mutation. So they would be on separate branches. Okay, if I look at the other two, this one has not only the G, but it also has a second mutation with a C here. So we know this one came after this one, which came after this one. All right, now this other one, we can see the T mutation, but we can also see another T mutation. So we know that this one came after this one, which came after this one. So just like the TV before, when we look at how they accumulated the remote control, the color, that kind of thing, we can see the same and build these cladograms here with DNA sequences alone. And that's the way many systematists, taxonomists are doing it nowadays. So tomorrow what we're actually do is give you another screencast on how to build a cladogram, and then we're gonna do a little practice with it. So I will see you then. Have a good rest of the day. Make sure you're getting outside these days and enjoying the nice spring weather we're having.